Okay, so we're going to start looking at section 15.1, which is on double integrals over closed rectangles, over rectangular regions. This graph we've got here shows a rectangular region, so we'll call it R. It's a rectangle, and that includes its interior, okay? And we'll say that it's a cross product, and this is not a vector cross product, but it's an interval on the x-axis, AB, a set of values, crossed with another interval, CD, on the y-axis. And so that notation just means the set of points, xy, such that x is between A and B, and y is between C and D, like that. So that's what that cross of two sets is defined as. Okay, so that's region R. Now we've got it all chopped up because we're going to integrate over a function of two variables, just in the same way that when we integrated a function of one variable over a closed interval, we chopped the interval up into subintervals. Here we're chopping a region up into subregions. Okay, and I need to be able to pick a point at every subregion and evaluate it. Evaluate the function at all of these points. So this first point here I'm going to point out is going to be in row 1, column 1. It's just a random point. Okay, and we'll call it x11 star, y11 star. So the 1, 1 stands for row 1, column 1. The star indicates a sort of a sense of randomness. And just to make sure you're on board, this is another random point here. And I think we'll call that one x row 2 column. So it'll be row 2, column 1, y21, both with the little stars, random point in these little subregions. Okay, the last one down here is going to be row M, column 1. So that's going to be xm1 star, ym1 star, like that. So way over here maybe you could label this point x1n, y1n, both with the stars, like that. So that's row 1, column n. Down here, we're going to have an x row m, column n, star, ym n star, like that. And then we'll just have a generic one in here. So this guy, we're going to call it row I, column j. So this is going to be row I, column j, and the point is xij. Still random, so with the star, and same thing with yij star. Okay. Try that again. Okay, so trying to get that moved out. That's better. Okay, so now what we're going to do is consider a surface that's defined over this region, and I've got one down here, so I'm just going to grab this guy down here and bring it up and just set it on this rectangle here. Okay, so that surface is going to be z equals f of xy, which is going to be assumed to be greater than or equal to 0. And I'll just say f of xy is greater than or equal to 0 on R. Okay. And what we do is we just evaluate the function of these two variables. We just evaluate it at each of these points, and I'll go ahead and plot points in all of these regions here. So basically we're evaluating the function at points in every one of these subintervals. Okay, like that. And then we find the volume of a prism at that point. So I am now about to set a prism in one of these subintervals, and I'll put it right there. Okay, and that thing's supposed to be touching the surface up at the top. So the point that's on the top of the prism here the x-coordinate is xij star. The y-coordinate is yij star. But then the z-coordinate, because z is f of xy, the z-coordinate will be f of xij star y of ij star. Okay, so there's your z-coordinate. And of course, that gives the height of that rectangular prism. And we have to find the volume of the prism and then sum this up for each of these subregions. And then we'll take the limit as the number of subregions goes to infinity, both in terms of rows and columns. So let's go ahead and say that the delta V is volume of the prism. Okay, so this is going to be, and we're going to have a delta x and a delta y here. I think that's pretty obvious. So let's make the small displacement here delta x, and then another small displacement in y, obviously delta y, like that. And so the volume of the prism is just going to be the base times the height. So the height is f of xij star yij star. That's the height times the base, which will be delta y delta x, which we may as well call dA. So we're going to have a delta A is just going to be delta y times delta x. Okay, so let's call this f of xij star yij star times delta A. Okay, and then the volume under this surface would be approximated by a sum of all the volumes of the prisms. So let's do the volume, the sum of the volumes of the prisms. So if you take total volume of all prisms, we would just take this quantity here, the volume of one prism, but then let the row and column vary and sum over each row and column. So you would do one sum, and first let's say where j goes from 1 to n, n being the number of columns, and then another sum where I goes from 1 to m, which is the number of rows. Okay, and that's the total volume under lots and lots of prisms that I am not going to draw. Okay, but maybe I could borrow a picture that I had prepared, so I'm going to go back to another document real quick. So that the total volume under many prisms under our surface here will approximate the volume under the curve, so under the surface. So let's go ahead and give a formula for the volume under the surface. So the volume under our surface, z equals f of xy, where x and y are in R. The notation for this is a double integral over R of f of xy dA. Okay. And this is just going to be the sum that we did previously, but then we're going to take a limit as the number of rows and columns both go to infinity. So let me just paste this in down here, and we'll add a limit as m goes to infinity and n goes to infinity. And that's just the definition of the double integral. Okay, so we've got the definition of a double integral here over a rectangular region. This is obviously not a way to evaluate a double integral with a limit on a double sum. That's not going to work. So in reality, you're not evaluating integrals this way. Of course, we're going to use the fundamental theorem of calculus because that's just how we do integrals in calculus. So there's a theorem called Fubini's theorem. So Fubini's theorem is kind of interesting. What it does is you pick either an x that's fixed or you pick a y that's fixed. So I think I'll fix y real quick. Well, I mean, it's easy. The picture will look better if we fix an x value. So let's pick a particular x, okay? And just say that that's somewhere right around here, okay? And the thickness, I'm going to do a little thickness of an interval down here, and I'll call it dx. So I think I'll do it this way. This interval's thickness is going to be dx, but the position is x. Okay, and what I want to do is I'm just going to take a slice of this thing. So let me make this nice and fat here. I'm going to do some big fat slices this way. Like this. And from the slices, we're going to go straight up to the curve and find out where it hits, find out where they hit the curve. Like that. Like that. Ooh, that's too fat. Okay, so I'm trying to come down and hit right there. And also this one. Yep. That's too thick. Like that. Okay, so here instead, what we're going to do is just to do the volume of this slice that I've created here, and I think I'll color that in a, ooh, not like that, in a blue maybe. This will be hideous. So it's still a volume because it has thickness to it. Okay. So let's just to do the volume of this slice for a fixed value of x. So maybe not with that color. So for a fixed x, the slice of thickness dx has volume well, I mean, you just do, maybe I'll bring this part over here. Has volume equal to, you just do the integral from c to d of f. And remember, x is just fixed. So the x is not a variable here. It's f of xy, which gives the height of the curve. And I'm just letting y vary. So this is the area. Okay. But I'm going to give it thickness dx. Okay. So we're just doing the area of one slice times its thickness. Okay. The total volume is the sum of all such slices where x ranges from a to b. Okay. Which is another way of saying that the double integral over r of f of x, y, dA could be written as a sum of integrals like what you have above, c to d of f of xy dy. Then to get thickness, we multiply by dx, and then we let x range from a to b. Okay, so we're just doing slices, giving them thicknesses, and then letting x vary. But there's nothing special about the order that I just did here. So first of all, I'm going to make this a little smaller. And say this is the same thing as the integral from c to d of the parentheses integral from a to b of f of x, y, dx. And yeah, dx on the inside, and then dy later. Okay, so I'll do dx there, close the parentheses, and say dy on the outside. And so those are just two, it starts as a double integral, and it's just saying you can nest two single integrals. So these are two regular integrals nested. We say they are iterated integrals. And with regular integrals, now you can apply the fundamental theorem of calculus as long as f is a continuous surface. And so we apply the fundamental theorem of calculus, part 2. As long as f of xy is a continuous surface. No tears, no asymptotes or anything crazy. On, I think the region was called R. I'm just going to check that real quick. Yeah, region R. So Fubini's theorem is there just to tell you could use the fundamental theorem of calculus with these things that we call iterated integrals. Okay, I'll take a second and see if anybody has any questions. It's 7:13. Let's do a few examples before we call it quits. There are some examples and a few properties. Okay, so this is just obvious. We're just doing the fundamental theorem of calculus. So first of all, note let's do it this way. The set of points x, y, such that a is less than or equal to x, less than or equal to y, and, oh, I didn't need to do that, less than or equal to b. And y is between c and d, so c less than or equal to y, less than or equal to d. Is often denoted A, B cross C, D. And those are not vectors, and this is not a cross product. Okay. I am not doing a very good job here. I'm going to try that again. I feel really bad. Okay, so this is just a compact way of expressing a rectangle. Any questions about that? Okay, let's do a real quick example. So, what you? So we're going to do a double integral of just 2x plus 1 dA over R, where R is a region, which is just going to be 0, 2, closed interval, across 0, 4, another closed interval. Okay, so that's a rectangle. Okay, so when you do the double integral of 2x plus 1 dA over R, you can rewrite this as an iterated integral. And it doesn't matter what variable you pick to go first. I can say 2x plus 1 and then do dy and then dx. Sometimes one order of integration will be harder than another. And by order, I mean you're doing y first here and then x because y is nested on the inside of this. Okay, so you can say dy dx, and if that's too hard, you can change it to dx dy. Sometimes one's easier than another. So let's go on. X again is going from 0 to 2. That's on the outside, but in the inside, y goes 0 to 4. Again, outside, x from 0 to 2. Okay. And now this is just iterated. So let's leave the 0 to 2 alone and take an antiderivative with respect to y. So that's going to be 2xy plus y. And now I usually like to tag everything with limits. So just, and you're going to see how I do this so that I don't get confused. If there's a chance of me being confused, I'll say what these limits are for. So these are limits for y. So sometimes I'll just write y equals 0 to y equals 4. So I don't end up substituting into the wrong variable, if you know what I mean. Because x is just going to sit there. You don't have to do that. If you trust yourself, you don't have to do that. I usually do it in a lecture so I don't confuse people. So that's what I have to work on first before I do the next integral. Okay. So I just might do, it's just a y, so I might do a 4 minus a 0. So this is usually how I would work it. I've got integral from 0 to 2. There's a 2x, and then y goes from 0 to 4, so I'll just do a 4 minus 0 there. And then plus y, that'll just be a 4 minus another 0. Okay, that's the x. So I think we've got 8x plus 4. Simple integral now. X. Okay, so now we can say that's 4x squared from 0 to 2 plus 4x from 0 to 2. So you get 4. Now this is x squared, so you're going to have a 2 squared minus 0 squared. And then plus 4 from 2 to 0. Sorry, 0 to 2, so it's 2 minus 0. So I think we're going to get 4 times 4, right? So 16 plus 8, is that 24? So how do you feel about that? It's easy, right? Nothing to it. I want to do one that's just a little harder, and it's going to be harder because I'm going to do a substitution to evaluate the integral. Okay, so let's try this one. Okay, so this one's the double integral of x plus y squared dA. And let's say it's over r. And once again, r is going to be a rectangle. So x is going to go from 1 to 3. And y is going to go from -2 to 1. Okay. And so easy enough, we can go straight to that with an iterated integral. So you're still integrating x plus y squared, but then, we did dy. I'll do, I guess I like doing dy first and then dx. So we know that y goes from -2 to 1. X goes from 1 to 3. Okay, any questions? Okay, and so, you can multiply this out. You could just say, oh, that's 1/3 x plus y to the third, holding x as a constant. You could do a substitution. I want you to I'm going to do a substitution so you can just see what they look like, because eventually I want you to see how these regions change when you do substitutions. So real quickly, I'm going to do, let's see, I've got x going, now I've got y going from -2 to 1. Okay, so let me show you here. Okay, so down below, I'm going to put -2 for y and then 1. And then, of course, x goes from 1 to 3 like that. And once again, this is not going to be very precise, so I'll do my best. So that's my rectangle. And you may as well see it. When you change variables by doing substitutions, the regions have to change with it. So this guy is called R. Okay. And I'm going to go ahead and do a substitution. So I'm going to say u is x plus y, just to show what happens when you do it. And d, remember, you're integrating with respect to y right now. So just ignore x. It's a constant. Du is just going to be 1. The derivative of x plus y with respect to y is 1 dy. So du and dy are the same. Okay. But you have to update the limits. So first of all, there's a lower limit. May as well look at it. So if u is x plus y and y is -2, then u is going to be x minus 2. If y goes up to its upper limit and is 1, then u is x plus y, so that's x plus 1. Okay, so the limits on u are not constants anymore. So just observe how the integral changes now. So we're going to have an integral. The integrand is really nice. It's x plus y squared, but that's just u squared. Dy, but dy is just du, like that. Okay. Now the limits on u are where it gets ugly. U goes from below x minus 2 to above x plus 1. So the limits on u are actually functions of the outer variable. The outer variable is x, so I'm going to put a dx here. And the limits on x go from, what were they, 1 to 3, like that. Inner limits can be functions of the outer variable. I'm going to make that a note. So the outer variable is x. Okay, any questions about that? So that's weird, and it's just a rule of thumb. You can't have a limit on u include a u, because you can't substitute u into itself as if somehow it changes into something else. You can't change like that. Okay, but you can solve a function of x into, there's a substitute a function of x into u, which is what we're about to do. So here I get the integral from 1 to 3. I'll just do 1/3 u to the third. Like that. But now u is going to go from x minus 2 to x plus 1. Like that. Okay. And then there's a dx. So in the end, this is just an integral in x. So you have an integral from 1 to 3. And I think I'll put the 1/3 out front, and then I'm going to have double nesting on it, x plus 1 to the third, minus with the lower limit, x minus 2 to the third, like that. And that'll be dx. Now, I'm going to just say this is not hard to evaluate, although none of us really wants to do it. So I'm going to put a ... there. And I do what's more important to me right now is what happens with the region that we changed to when we were integrating. So real quick, notice the following. I'm going to go ahead and have a plane here. X is still going to be the independent variable, but u is put in place of y because I changed my variables. Okay. Now I know x goes from 1 to 3 still. So I'll go ahead and put that back down, 1 to 3. But the limits on u are functions of x. U goes from x minus 2 in the lower limit. I'm going to have to slide my x-axis up because I need an intercept at a -2. Okay. So on the bottom, u is x minus 2. So I've got my -2 here. And I'm going to go ahead and draw like a u equals x line like this. Let me see. What's the x? I'm thinking about what the x-intercept is. If u is 0, x is 2. So this is going to cross like this. Okay, and then at 1, and so that's that line right there is u equals x minus 2. Okay, and then u equals x plus 1 is the upper limit. So let me put a 1 up here. And I'm going to draw a parallel line because it has the same slope. Like this. Okay, now x still goes from 1 to 3. Let me put dark boundary around this so it's absolutely clear what's become of our region that we were integrating over. Okay, I would call this S. It's a little more tricky. Okay, so S is the is a transformation of R. that occurs after a change of variables. Running out of space here. So I'll rearrange this a little bit, but let me go ahead and put my notes in after a change of variables. Okay. So, and this is going to have ramifications with some of the other, the work we do whenever we change variables. It can get weird. And so I want you to just keep in mind, in the back of your mind, this picture that when you change variables, you are changing the region. You have to update the limits on your integral. And updating the limits means your new variables are ranging differently than the original variables did. And that changes the geometry of the problem. And that becomes an issue if the region gets much bigger or much smaller. You have to deal with that. Okay, so I want to go ahead and let's go ahead and take our break now. And we'll pick this up in 10 minutes at, let's say, 7:40 in the 43. Okay. So I'll see you in a bit. Well, I'm back. Hope you guys are doing all right. There's a bunch of rules for integrals. Some stuff about average values. I'll let you guys read that. I guess most of the rules come up in 15.2. Just double checking. There they are. Okay, not till 15.2. So I'll make a list of those. I think I did all this with simple. I'll go ahead and finish this integral here now that we're all back. And this is a good way to kill time. Can you guys see this? Oh, you can't. I'm not moving. So let me restart. I have to start my share again. Hello. So let's see if this works. Okay, so I decided I would go ahead and finish my integral here. So I've got a couple things going on here. Probably maybe split this into two integrals because I'm going to do two different substitutions. So on the first one, I'll do, let's see, 1/3 integral from, that's not 1 to 1, it should be 1 to 3. First integral, x plus 1 to the third, that's a dx, minus the next integral from 1 to 3 of x minus 2 to the third. So I'll have v be x plus 1, and dv is dx. And then over here, let's do w is x minus 2. So dw is dx. So I think we can easily update these. Right, so so we have a 1/3 integral of v to the third dv. When x is 1, v would be x plus 1, so that's 2. When x is 3, I guess v would be 4. And then minus the integral of w to the third dw. And when x is 1, w is negative 1 because it's x minus 2. And when x is 3, w would be 1, I guess. Okay, so that's easy. Oh, but there should be 1/3 in front of both of these. So you're going to end up with 1/12 b to the fourth on both of these with different limits. I think this part's going to be 0. Because you get 1 minus 1. Okay, so here we're going to get 1/12 4 to the fourth minus 2 to the fourth. Eek. I don't know what that is. I'm just going to do that on a calculator. I should know what 16 squared is. Is that 256 minus 16? So that's 256 minus 16 is 240. Yeah, 240 divided by 12 is 20. This whole thing comes out to be just 20, I think. Let me check my notes. I got 24 last time I did it, and that's... Oh no, that's a different problem. Yep, got 20. That's a good answer.